we got moderators, right, throughout the day. You've met most of them. Oh, well, I'm sure most of them, but you've met some of them. And as I said, one moderator fell through, and one of the moderators for this afternoon on the DevOps track is Michi Verhas, who has the same last name as our next speaker. And that is not a coincidence, actually. So Peter Verhas and Michi Verhas, they're dad and son, and they're both at the conference in 2 different capacities. And Michi jumped in to help me with this, and this is going to be really cool, because look, here's Peter. Oh, damn. And there's Michi. No, he's in the middle. Can each of you point to the other?
Hello.
And that's unfortunate. The unfortunate thing about StreamYard is that I cannot rearrange you now. You should definitely, because now to one another, you're going to look into like the outwards directions. Anyway, that's all. I'm going to leave it up to Michi to introduce his dad, and then he will play the talk, and everything will be normal, except that both of them literally sit in the same room next to one another, and that's pretty cool. So I'll leave you to it. Have a lot of fun. Bye.
Okay, so I'm Mihai Verhas, and I'm going to be moderating this talk and the question and answer session after it. And as Nikolai said, I'm Peter's son. Okay. And not much else to say. I think Nikolai filled the time in perfectly well, and that probably left enough time for people to join us. So I'm going to ask you to introduce yourself. Sorry, I'm looking the other way always because the camera works in mirror. Sorry. So please introduce yourself, Peter.
My name is Peter Verhas, and I think there is some slide in the presentation that will where I introduce myself. So you may hear it twice, but I'm a senior developer with more than 25 years of experience. Actually, it's, if I am counting the very first program, then it's 35 years. So last time we decided with my boss that when we were approaching a client that we don't try that, because then that's too much. So we just decided that more than 20 years of experience, let's say that. And the presentation is going to be about value types and Go language, which is an interesting thing to compare the two. And I know that it's very popular because 2 years ago, I wrote an article about, it's in this environment, we have some trains coming by sometimes, but the presentation is fairly noise-free because it was recorded. And if you listen very carefully, I know that at some place there are some dogs barking, but never mind. And 2 years ago, I wrote an article about comparing Go language and Java, and actually it was republished on DZone. And even though usually 5,000 to 10,000 people are reading my articles that are published there, more than 100,000 people were reading that. So let's go ahead and let's listen to this presentation. This presentation is about Java Go language, comparing them from the perspective of Java value types. My name is Peter Verhas, and I am a Java senior developer with more than 25 years of experience. I work for the company called EPAM. I publish a lot. It is my passion. You can find articles on my blog. You can read my books I published with Pact. You can find videos recorded, different conferences, and I have several open source projects. If we want to compare Go with Java from the perspective of value types, as the talk's title suggested, then we have to know the answer to 3 questions. The first, what is value type? The second, what is Go? And last but not least, what is Java? Although I hope that this last part does not need a lot of explanation at this conference. In this presentation, I will focus on these 3 areas. If you like, This is the agenda of the coming half an hour. Let's talk about our first topic, value types. Value type is a feature that does not really exist in Java yet, but it's planned and actively developed. There is a project codenamed Valhalla aiming to develop value types. It was started in 2014. That is already 6 years. By now we have pre-release versions that we can try. It's a long time in development. Introducing value types into the Java language and into the Java infrastructure is not simple. It is complex, even though Java already has something that is like value types. Primitives like byte, short, and long, and so on are actually value types. This is what the project aims to extend. We want to have user-defined value types. We want to have simple structures, like Java util date stored in variables. After all, the size of a Java util date is the same as the size of a long. Why do we have a primitive value for one and not for the other? This is what we need value types for. When we have value types, then we can store compound structures in value type variables instead of having a reference to an object. There are many implications that come from this. A value type cannot be null. Just think about it. If it is the value itself and not a reference. An integer with capital I is an object, and an integer variable stores a reference to an object. It can be null. On the other hand, an int variable stores the int value, therefore it cannot be null. The value of a value type cannot be modified. It is essentially immutable. This is a little bit difficult to comprehend at first because the variable that stores the value is not immutable. On the other hand, the value is absolutely immutable. For example, you can have an int variable that stores the value 1. You can modify the variable to store the value 2. It is absolutely okay. However, you will never change the value 1 to be 2. This would be nonsense. Similarly, when we have a user-defined value type, the variables storing a copy of the value can be changed, but the value itself is immutable. Comparing is done via the double equal sign operator. There is no complex logic comparing them. The values are compared bit by bit. For the types themselves, there is no inheritance and no polymorphism, just as there is no inheritance and polymorphism in the Java primitives. To be honest, it could be possible to have inheritance, but definitely no polymorphism, and, well, if we do not have polymorphism, then inheritance is only syntactic sugar. Last but not least, the values are passed by value in case of a method call. This is not a surprise. All method calls in Java use pass by value, although the value that we pass is a reference. Can be confusing when coming from a language that have pass by reference method calls and or pointers. This all can be paraphrased that a value type codes like a class, but works like an int. This is all nice and very technical, but why do we need value types? Just to make the language more complex? Why do we need it now, if we did not need it during the last 25 years? These are the questions that many times I get from my colleagues when I'm talking about value types. The last question is the hardest because it implies that we did not need value types. We actually did need them. We just did not have them. Having nothing better, we had to use objects instead, even though not everything has to be an object. For example, we do not need synchronization on everything. We are happy without synchronization. For example, when using primitive double values. Similarly, we do not need references to everything. For example, we do not need references to primitive int values, or for that matter, to a double, to a long, or to other primitive values. And we definitely do not need 16-byte headers for each and every chunk of data that we handle currently as an object. We, the programmers, do not need it. The Java VM needs it to operate properly, not us humans. In many cases, we would be better off without objects. The objects are stored on the heap, and when they are not needed anymore, they have to be collected by the garbage collector. Not always. Sometimes objects are stored on the stack. Yes, I know. In some cases, objects can be allocated on the local stack of a method when the escape analysis implemented in the just-in-time compiler realizes that the object cannot escape the scope of the method. But if ever the reference to that object is passed to a method one level deeper in the call chain, then the JIT just must assume that the reference has escaped and it will allocate the object on the heap. On the other hand, an int or long, even if the value is passed to a method done on the call chain, will be stored in a local variable on the stack. That is because they are value types. They are copied and never referenced. As a matter of fact, value types are not only can get on the stack easier, they are by default allocated on the stack if the just-in-time compiler thinks that is the best way to store the values. Also, value type arrays are CPU friendly. When you have an array of Java util date objects, then what you actually have is an array of references to Java util date objects. The actual objects can be scattered in the memory at different locations. When we loop through an array from the first element to the last, the CPU moves the memory page where the first element of the array is to the CPU cache. When it needs to access the second element, it is already in the cache, and so on. In case of an object array, what the CPU moves into the cache is the array of references. Then it has to move the first object into the cache along with some other data that is on the same memory page. Then it uses the second reference, which is already in the cache, but the referenced second object is not necessarily on the same page as the first object. The objects can be scattered all over in different locations. It means that each time the loop goes forward, the CPU has to read the memory, which is 5 to 10 times slower than reading from the cache. On the other hand, an array of value types is an array that contains the values one after the other. When the first one is moved to the cache, then the second, the third, and so on are also moved into the CPU cache so long as they are on the same memory page. After the first element was processed, accessing the second is fast because it is already there in the CPU cache. Perhaps this is the most important advantage of value types when we are having an array of them. What is the speed and the memory gain that we can have when we use value types? Let's have an example where we handle 1 million Java util date objects. It may be a rare situation that we need so many objects, but you can imagine just anything instead of a Java util date. That is not too complex and relatively small structure. Java util date is an example only. The date itself is the same size as a primitive long. That is 8 bytes in Java. In addition to that, we need a reference, technically a pointer, in the array that points to the objects. This is again 8 bytes. And every object has an object header, which is 128 bits. In other words, 16 bytes. In case of 1 million dates, we will have 8 megabytes of data and 24 megabytes of administrative data that we do not need. It is needed only by the GVM because it handles only objects and not value types. If we use value types, then we free up 24 megabytes of memory. This is a significant amount. The gain in speed can be even more drastic. To understand the speed advantage, we must look at how computers and CPUs work. A really fast CPU these days has a 4 GHz clock rate. It means that one cycle is 0.25 nanoseconds or 25 picoseconds. This is the time needed for the simplest, fastest operation. For example, moving the value from a register to the arithmetic logical unit that can perform operation on the value. Light in a vacuum travels only 7 centimeters during this time. Why do we care about the light? Because that is approximately the same as the speed of the electronic signal that moves data inside the processor and between the processor and the memory and other peripherals. In reality, the speed of the electronic signal is a little bit less because of various factors like conductor resistance and dielectric parameters of the printed circuit board and generally physics. For us, it's a good approximation to think about the speed of the signal as the speed of the light. When the CPU reads something from the memory, then the addressing has to travel from the CPU to the memory chip on the motherboard, and the data has to travel from the motherboard to the CPU. The travel itself takes time, plus the time needed for the CPU and the memory chips to do the addressing, data selection logic inside the chip. The second part can be optimized on the hardware level, but the distance between the memory and the CPU is a hard limit. You can move part of the memory onto the CPU chip, but you cannot move all the memory into the CPU. The memory that we move onto the CPU chip is the CPU cache. The CPU has different caches that are usually called L1, L2, and L3 cache. L1 is the smallest but the fastest cache, and L3 is the largest but slowest cache. In this case, even the slowest is extremely fast. Level 1 cache size is usually a few kilobytes, like 24 kilobytes, and the access time is less than 1 nanosec. Level 2 cache is a bit bigger and already needs almost 3 nanoseconds to get data from. Level 3 cache is still on the CPU, and it is already 70 times slower than the level 1 cache. If we want to read something from the memory, that is a factor of 400 times the speed. Now let's make a very simple calculation. We have 1 million Java util date objects or value types, each being 8 bytes of valuable data. We want to iterate through these values in loop and do some calculation. The L1 cache can accommodate 8,192 of them. If we use value types, then we can read the array into the cache in 122 batches, each time reading 8,192 of them. This is 122 memory reads and 1 million cache reads. That is 12,200 nanoseconds memory reads and 900,000 nanoseconds cache reads. The total is 912 microseconds. If we use objects, then all the reads may happen to access to the memory summing up to 100,000 microseconds. The speed gain is 100 times faster execution. In real life, the speed gain may not be that much, as the objects may not be scattered so random in the memory, and there are also level 2 and level 3 caches, but still, the speed gain is enormous. Now, we go to the second topic, the Go language. Go is a system programming language. It is a compiled language like C, and there is no virtual machine whatsoever that runs the bytecode. There is no bytecode. It is compiled directly to executable. It has a garbage collector implemented into the language, so there is no need to worry about allocations and deallocations. It was and is continually developed by Google to develop the software that run their servers. It is an object-oriented language, and at the same time it is also functional. In this presentation, I will not talk about the functional part of it, and I will discuss the object-oriented features as much as it concerns us only. Why should we be interested in Go? Because it's a cool and very powerful programming language for some of the problems we may need to solve. But for now, for the purpose of this talk, because it has some memory structures that are very different from those of Java. Go does not have classes and objects. It has structs. Yes, it may be familiar for you from different languages, starting with such ancient archaeological ones as C. A struct is stored in the memory, but it is not an object. It does not have a header. It is only the bare data. If we have an array of struct, then it is not an array of references, it is an array of the data blocks. Does it ring a bell? Very similar to what I was just recently explaining about Java value types. What is different from Java value types is that there can be a reference to a struct in Go. To be more precise, it's not a reference, it's a pointer, but there is no inheritance with structs. Very much like in case of value types, but don't worry too much about object-oriented programming, even though we have learned in school that the basic building stones of object-oriented programming are inheritance, polymorphism, and encapsulation. It is still possible to have it, replacing inheritance with a different relation, containment, as we will see. And Go has interfaces, but this is something totally different from a Java interface. It is a type that has no implementation. Variables can be declared to be of the type interface, and in that case they behave differently. Let's have a look at some sample code just to get the taste of Go. And because you are all seasoned developers, we start in the middle with something that is more than just a hello world. We define a struct that has one int field. The name of the struct is myStruct. The function named myFunction works on a struct myStruct. It is the receiver of the method. In Java term, this reference to the current object that the method is running on. By the way, do you happen to know that since Java 8 you can specify the receiver as an optional first argument to an instance method and to non-static inner class constructors? The return value of the myFunction is a function itself. The return function, when called, returns an int. The function main initializes the struct myVariable x with a structure that contains the field I with the value 42, then calls the function myFunction on the variable x, and then it calls method that it returns and then prints the value. What we have seen here is a struct definition, a method that works on this struct, a function returned from the method, and the main function that is executed like the Java public static void main when we start the code. The first example is just a warm-up. To raise the bar to the level that helps us understand how Go language structures and object orientation works, we need a more complex example. In this example, we demonstrate polymorphism. We have two structures and there are two methods named myFunction, one working on one of the structs, the other working on the other struct. There is an interface type declared that says that any struct that has a function named myFunction with a matching signature implicitly implements this interface. In the function main, the reference x is declared to be of this interface type, and thus it can hold a reference either to myStruct or your struct. The structs do not implement the interface explicitly, There is no implement keyword. They just do implement. The third example demonstrates containment. This is what Go has instead of inheritance. Here we have two structs, just like in the previous example, but in this case the second struct contains the first one. The my function is implemented only on the struct my struct and not on the your struct. Still, the interface that requires that the struct has a my function method is implicitly implemented by both structs. That is because the struct your struct contains a my struct, and through that it implements the inherited function. When the variable x references a your struct, calling the my function method on that reference calls the function passing the instance of my struct contained in the struct your struct in the receiver. In Java, when there is a class that extends another, then calling a method on the child class will work if it inherits the method from some of the parents. The receiver, however, is always the child object, and in this case the variable type is an interface, or one of the superclasses. The JVM still knows the actual type because it sees that from the header of the object that has a class pointer. In Go, the call is not passed to parent, but rather the code invokes the method using the embedded internal contained struct. When the call is executed, the code knows the actual type in case the variable is of struct type because there is no polymorphism. Polymorphism in case of Go exists only when the variable we use is of interface type. The class pointer is the pointer that identifies the actual type of an instance. It is in the header of the object, thus the JVM always knows the actual type of an instance during runtime. The variable has a reference to an instance and the instance has a header with the class pointer in it and the data itself. If the variable is of the type of an interface, that is a compile time concern mainly. In Go, this is a little bit different. A struct variable is not a reference. The class pointer or struct pointer does not exist. This is a compile time information that the compiler works with, and during runtime the code implicitly knows the actual type stored in the variable. The interfaces that are declared in the source code do not exist in the compiled code or in the memory. They are only compiler concerns. However, this is totally different in case of a variable that are of interface type. An interface type variable has two pointers. One is a pointer to the data. The data, however, does not have a header in Go, and thus there is no information in it about the structure of the memory, including the size and the fields in it. The code should know the actual type of the structure, which in this case cannot be known from the compilation. In this case, the variable has another reference to a descriptor that describes the structure. That way, the running code always knows the type of the referenced structure. It is either known since the compilation time or it is known from the interface variable reference. Although it is not strongly related to this topic, there is something very interesting in this type of structure. An interface variable can be null and still having a struct reference in it, and thus can be used to call a method on it as a receiver. That way, strangely for Java developers, this reference pointer can happen to be null or nil, as Go names the null pointer. Now that we have discussed just enough Go, we can compare the struct type of Go and Java value types. They are not the same. There are significant differences. For example, Go structs can be referenced and are mutable. There is also a kind of inheritance, and there is polymorphism through interface variables. Java value types do not have anything like that. They could, but they are designed not to replace classes and objects. They will be there to extend the possibilities. From the programming point of view, when the expressiveness of the language is concerned, there is no problem with Java. The aim for value types is to help the compiler, to create better execution. There is one question left for our topic in this talk. How will value types be implemented in Java? Or rather, how are they implemented in Java using present tense, as we already have pre-release versions that we can play with? The simplest implementation of value types is to add a new flag to a type in the bytecode that signals that the type is a value type, or value class to use a different name. The execution can still store the value in an object instance, simulating the value typedness of the instances. It prevents null value, even though technically there is a reference during the execution. The compiler and the JVM will not allow an immutable operation on the value class instance. The compiler will not allow inheritance and polymorphism. The method calls will create a new copy of the instance and pass the reference to that instance. Essentially, we are simulating value types using plain old Java objects. Shocking, is it? Why was all this buzz, all the different arguments about simplified escape analysis, early CPU cache friendliness, and the promise that all these will result less memory use and much faster speed? We just end up with some fake value types that are essentially plain old objects. Yes and no. Yes, because this way we can keep all the good things that objects have, for example, backward compatibility, when suddenly Java util_date becomes a value type and your code as it is written 20 years ago still works with it. And no, it's not just a fake object/class, because it has some special features. Rules like being passed by value that makes optimization of the storage possible. And the optimization is not done on the bytecode level. It never was. It is done by the just-in-time compiler, and the just-in-time compiler does that very much, even in the pre-release version. What is left for you after this talk is to visit the page JDK Java Net Valhalla, download and install the early access version, copy some demos, perhaps modify them, compile and run. You can also run some micro-benchmark to see how value types are faster than plain old Java objects. Value types are not objects. They are something like structures, more efficient memory storage, and they are here knocking on our door. This feature closes a gap that exists between Java and other languages. With value types, we will be able to use the memory more efficient and faster, and it will not be radically different programming style like it was for streams or Lambda. And since pre-release versions are also available to play with, and because this talk was comparing value types and Go language struct data structure, what else could I say that? Go for it. Find me at peter_verhas@epam.com. Follow me on Twitter, LinkedIn, GitHub, read my blog articles at javox0wordpress.com, and generally just keep in touch.
We have time for some questions. If anyone has some questions, please write them in chat, and I will ask the best questions to Peter, and then he can answer your questions about value types or anything really related to the talk. So my first question would be, if I used reflection on value types, would I know, is that information stored about value types? Like, would I know that the thing that I'm working with currently, like a field or, say a field. So I ask for declared fields in reflection, and I get back a value type, would I know that it's a value type, or would that still look like an object, a class, or an object? Yeah.
Well, I think the answer is that you can do the same thing that you can do with the primitives, except I get the point that the primitives do not have fields inside, and value types do, and I was not looking at it, so I cannot tell you the answer about it. Since there is no possibility to do inheritance with value types, and when you're querying something which is a value type and there is no reference to a value type, anything that you could do on an object using reflection can be done on value types during compile time. So there is no way to query the structure of a value type through reflection. It's illogical. I don't know if there is anything like that or there is not, because I've never tried it with the pre-release version. And but there is no point to do that, because when you have a variable which contains some value, then what's inside is given, and you cannot intermix them, and you cannot have a variable which stores a value type and not know what value type it stores, because it should be known by compile time.
Okay. Here's an interesting question. What exactly is the difference between the records introduced by Java 14 and value types? What's missing for records to be value types?
Okay, records is kind of syntactic sugar, because they can be used to describe a special class which is actually just violates encapsulation, which stores only the data, and the code that's working on it is separate. And it defines that it has final fields and things like that, but it's an object, it's a class, and you can have a reference to it. You can pass it by passing the reference to it. So the variable is always passed by value when you have a variable that holds a record, but you are the method to which you were passing the record will work with the same record and not a copy of the two, as in the case of value types. So records can be fairly large. Value types shouldn't be. There is no limit for the number of the fields for value types, but still, if you have something that has like hundreds of fields, then probably it's not a value type, and the value type is not the thing that you should use it for. Value types are much for, and let me skip on to the next question. For what would you recommend to use value types? Value types are for things like when you have something which is a compound structure, so not just an int, not just a Boolean, but something that has a few fields, and you have a lot of them in an array, and then you work with them so that they are in the memory, and then they are stored in a continuous memory area, and then you have to loop through it in a stream or for loop or whatever, and then it's much faster to go through them. Right now, you cannot do that. Right now, what you can really do is that you just store it in a byte array, and constantly you convert back and forth between the byte structure and your actual values, and then it may still be faster with this conversion than having separate objects everywhere in the memory, and then always fetching here from there from a non-processor cacheable way these values. And this is something that somebody has to do sometimes today with Java if they have a lot of objects like that, and the performance is very important. As the sample calculation said, it was 100 times slower if I always have to fetch things from the memory. And what happens when a value type instance is referenced? There is no reference. And if it's in a closure, then it's a copy. It's never passed by reference. If it's used in a closure, then it's a copy. And if the call stack disappears, then the value type copy disappears, but the other one, which was copied to the other part, it's there. So it's the same as if you have an int variable and you are referencing this int variable, and similarly, because value types are immutable, probably you should have an effectively final int. Think about an effectively final int, and it's referenced in a closure, in a lambda, essentially. Then the variable itself from the stack, local variable, may disappear. The value is still there.
Value types are basically, is there any difference between a value type and the primitive? Basically, value types are write your own primitives then?
Kind of, yes. And not really, because primitives are primitives, but yes, kind of things, yes. And the example is the date, which is a very good candidate for becoming a value type. And will generics be verifiable when value types are introduced? That's a very interesting question. And if you dig deep into that, then you have to think about how it works. And you can see other languages like C# that does it. And currently, you cannot have generics with primitives like int, boolean, double, with the lowercase double and lowercase boolean. And the reason for that is that if you have a code which can be parameterized with these types, and this code is working with an array of these, then the size of the array depends on the size of the type itself. If it's a class, then it's an array of references. And the actual code, when it's indexing the array, doesn't need to know what it is indexing, what it's referencing. But if the generic is of a value type, and then you call the class or create a class which is a generic, or a method with has a generic parameter of a value type, and it works with an array, and you want to fetch the second element of the array, then you have to look at the memory location, which is as many bytes from the start as big the value type size is. In case it's an object, then it's just the next reference. The reference is, depending on the 32 or 64-bit implementation, is 32 or 64 bits, so 8 bytes in the 64-bit JVM. How does the C# do it? Well, actually, when you call it during runtime and then it sees the size, then the bytecode is recompiled for that very special size. And then it knows that what is the size of that value type. And they call it different. I think it's struct in C# case. And it's not so simple. So probably there is, as far as I have heard informally during the conferences, there are intentions to do this later on and to develop these things. But currently, it's not there in the early release, and do not expect that it will be there soon. But I think sometimes in the future there will be.
Many Java APIs are based on generic type parameters which derive from object. As values are not objects, will you be able to use generics at all?
Not in the first. So there will be no generics for the value type. So you cannot use value types as generic parameters, just as you cannot use int as a generic parameter. You can use integer. Also, you ask whether you pass an array of value types into a method, is the whole array copied? It's very easy to answer. Think about an array of int that you pass. That's an object. Then you pass the reference to that object, not the int, not the copy. If you pass an int to a method, then the value is copied. The value of the int is copied. The number is copied. So the answer is no. If you pass an array of value types into a method, then the whole array is not copied.
Thank you very much, and goodbye.